I am Madhuchelvi, Associate Professor of Mathematics, Sri Sharada College for Women, Salem. Today, in this session, I am going to discuss about linear transformations, especially the unitary, Hermitian, and normal linear transformations. First, let us define the vector space, the inner product space. The vector space V over F is said to be the inner product space if there is defined any two vectors u comma v belongs to V, an element inner product uv belongs to F such that uv equal to vu the whole bar and inner product uu equal to 0 if and only if u equal to 0 and inner product uu greater than 0. Alpha inner product alpha u plus beta v comma w equal to alpha u comma w plus beta v comma w, where alpha beta w belongs to F. Let us see a lemma. If T belongs to A of V is such that the inner product Vt comma V equal to 0 for all V belongs to V, then T equal to 0. See the proof. Given inner product Vt comma V equal to 0 for every V belongs to V. Then if you take instead of V u plus W for some u comma W belongs to V, we get inner product u plus W of T u plus W equal to 0. This implies the inner product ut comma wt comma u plus w equal to 0. We can write this as inner product ut comma u plus ut inner product ut comma w plus inner product wt comma u plus inner product wt comma w equal to 0. By the hypothesis, uh, ut comma u inner product ut comma u and the inner product wt comma w equal to 0. That's why we get only the inner product ut comma w plus inner product wt comma u equal to 0. Let us call this as equation 1. Now in this equation 1, replace w by iw, where I squared equal to minus 1. Then we get the inner product ut comma iw plus inner product iwt comma u equal to 0. If you simplify by using the facts that inner product ut comma iw can be written as minus I comma minus I ut comma w and iwt comma u equal to I into inner product wt comma u. Using this we get minus I of ut comma w plus I into inner product wt comma u equal to 0. This gives minus of ut comma w plus wt inner product wt comma u equal to 0. Now if you add 1 and 3, we get 2wt comma u equal to 0 implies the inner product wt comma u equal to 0 for every u comma w belongs to V. Since it is true for every element, it is true for wt also. So we get inner product wt comma wt equal to 0. By the definition of the inner product, u comma u equal to 0 implies u equal to 0. So wt equal to 0 for every w belongs to V. This implies that t equal to 0. So we proved the lemma. Next, let us see one example. Let V equal to the set of alpha comma beta, where alpha beta are real, where the inner product is a dot product. Here, the inner product is defined as a dot product. Let T be the linear transformation, sending the inner product alpha beta to minus beta comma alpha. Since t not equal to therefore t not equal to 0, because it sends alpha beta to minus beta alpha. So if alpha beta not equal to 0 means that minus beta alpha also not equal to 0. So t not equal to 0. Let V equal to the inner product alpha beta, where alpha not equal to 0 and beta not equal to 0. But the inner product Vt comma V equal to the inner minus of what is Vt? Vt is we are getting that alpha beta 2 minus beta alpha. So alpha beta t alpha beta. So minus alpha beta my alpha beta. So minus beta, it is inner product is defined as a dot product. That's why minus beta alpha plus alpha beta, that is equal to, since alpha and beta belongs to the F, the field, so commutativity exists. So we can write minus alpha beta, that is equal to 0. So Vt inner product Vt comma V equal to 0, but T not equal to 0. So the converse of the above lemma is not true, is shown by the above example. Next, let us see one definition, that is unitary definition. The linear transformation T belongs to A of V is said to be unitary if the inner product ut comma vt equal to the inner product u comma v. For every u comma v belongs to V. Let us see another lemma. If the inner product Vt comma Vt equal to the inner product V comma V, for all V belongs to V, then T is unitary. So it is the necessary condition for the linear transformation is unitary. Proof: let the inner product U comma V belongs to V. Then U plus V comma T, U plus V of T, U plus V of T equal to, by the hypothesis we get U plus V inner product U plus V comma U plus V. Then we can expand this as inner product ut comma ut plus inner product ut comma vt plus inner product vt comma ut plus inner product vt comma vt. But we know ut equal to ut comma ut equal to u comma u. So using that hypothesis, we get inner product u comma u plus inner product ut comma vt plus inner product vt comma ut plus the inner product v comma v equal to, we can write it as u comma inner product u comma u plus u comma v plus v comma u plus v v. This implies ut plus vt plus vt plus ut equal to u u comma v plus v comma u. Replace v by iv in equation 1. We get ut comma ivt plus ivt comma ut, that is equal to u comma iv plus iv comma u. That implies minus I of ut comma vt plus I of vt comma ut equal to minus I of u comma v plus I of inner product v comma u. This implies inner product minus of ut comma vt plus vt comma ut equal to, that is we are cancelling I both sides, inner product uv plus inner product vu. So if you subtract 2 from 1, we get 2 ut inner product ut comma vt equal to 2 inner product u comma v. We get this implies ut inner product ut comma vt equal to inner product u comma v. So it is by the definition we get T is unitary. So the necessary condition for the transformation is unitary is if Vt comma Vt equal to V comma V, for all V belongs to V, then T is, it is the condition for that, because by the definition we get it is unitary. Let us see a theorem. If the linear transformation T on V is unitary, if and only if it takes an orthonormal basis of V into a orthonormal basis of V. So it is the necessary and sufficient condition for a linear transformation is unitary. Let us see the proof. Suppose that V1, V2, etc. Vn is an orthonormal basis of V. Then by the definition of orthonormality, inner product Vi comma Vj equal to 0 if I not equal to 0, I not equal to j, and inner product Vi comma Vi equal to 1. So we have to show that if T is unitary, then the set V1T, V2T, etc. Vnt is also an orthonormal basis of V. But VIT, VJT, inner product VIT, VJT, by the definition, we get inner product Vi, Vj. But what about inner product Vi, Vj? Because Vi, Vj are orthonormal basis, elements of orthonormal basis. So we get it is equal to 0 if I not equal to j. So Vit, Vit equal to Vi, Vi. Conversely, if T belongs to A of V. So we are taken that it is an orthonormal basis, and we proved that it takes an orthonormal basis to an orthonormal basis. Conversely, we are assuming that T belongs to, if T belongs to A of V, both V1, V2, etc. Vn and V1T, V2T, etc. Vnt are orthonormal basis of V. Now we are going to prove that T is unitary. So for let us take two elements U comma W belongs to V, then U equal to, we can write it as using the basis summation I equal to 1 to n alpha I Vi, W equal to summation I equal to 1 to n beta I Vi, where alpha I comma beta I belongs to F. Then the inner product U comma W equal to, by using the property of inner products, we get summation I equal to 1 to n alpha I beta I the whole bar. However, ut equal to summation I equal to 1 to n alpha I Vi of t, that is equal to summation I equal to 1 to n alpha I of Vi of t. That is Wt equal to summation I equal to 1 to n beta I Vi comma t, that is equal to summation I equal to 1 to n beta I of Vit. Therefore, V1t, V2t, etc. Vnt is also an orthonormal basis. So then ut comma Wt equal to summation I equal to 1 to n alpha I beta I bar. This implies ut comma Wt equal to u comma w. So it is unitary. So we prove the two implications also, the necessary part and sufficient part for a linear transformation is unitary. Let us go to the next lemma. If T belongs to A of V, then given any V belongs to V, there exists an element W belongs to V depending on V and T, such that inner product ut comma V equal to inner product u comma d for all u belongs to V. This element W is uniquely determined by V and T. Let us see the proof. Let U1, U2, etc. U and be an orthonormal basis of V. We define W equal to summation I equal to 1 to n UIT, inner product UIT V whole bar into UI. Then UIW equal to 1 when inner product UIT comma V the whole bar. So the inner product UI comma W equal to the inner product UIT comma W. Implies W is an element depending on U, such that depending on what is that, it is depending on V and T, such that UT, inner product UT comma W equal to U comma W. We have to prove that W is unique. Suppose that W1 is also an element of V and T, V and T, such that the inner product UT comma V equal to U comma inner product U comma W. This implies UW, inner product UW equal to UW1. This implies inner product U comma W minus W1 equal to 0, implies W minus W1 equal to U. This implies W minus W1 equal to 0. This implies W is equal to W1, that is W is unique. Another definition is Hermitian. So T belongs to A of A, then the Hermitian adjoint of T, written as T star, is defined by inner product ut comma v equal to inner product u comma v T star for all u comma v belongs to V. And the next lemma tells us about the properties of the Hermitian adjoint. That is, T star of star equal to T. And second one is S plus T whole star equal to S star plus T star. Third one, lambda S whole star equal to lambda S star. Fourth one, ST the whole star equal to T star into S star for all S comma T belongs to AFE and all lambda belongs to F. This proof is very straight and very easy to understand. So we can go to um, the next lemma. If T belongs to A of E is unitary, if and only if T star equal to 1. Let us see the proof. Suppose that T is unitary for every inner product u comma v equal to v, u comma inner product u comma v T star equal to, because T star equal to 1. So the inner product u comma v T star equal to ut inner product ut comma vt, that is equal to u comma v. So u comma v T star equal to u comma v implies T star equal to 1. The converse part is, assume that T star equal to 1, the inner product uv equal to u comma inner product v T star. That is ut comma vt implies T is unitary. Now let us see the Hermitian linear transformation definition. T belongs to A of E is said to be Hermitian if T star equal to T. Like that, if T star equal to minus T, then T is called skew Hermitian. Next, let us see the definition of normal linear transformation. If T belongs to A of E is said to be normal if T star equal to T star T. Then that is the definition of normal linear transformation. Let us see a lemma on normal linear transformation. If n is a normal linear transformation and if Vn equal to 0 for V belongs to V, then Vn star equal to 0. That is, consider Vn star comma inner product Vn star. That is equal to, we can write using the inner product properties, inner product Vn star n comma V, that is equal to Vn n star V, that is equal to Vn star inner product comma Vn star, that is equal to 0. The 0 implies Vn star equal to 0. So n is a normal linear transformation, and if Vn equal to 0 means that Vn star also equal to 0. Finally, let us see the properties of linear, unitary, normal, and Hermitian linear transformations. Say, first, let us say the application of Hermitian linear transformation. That is, it is applied in quantum mechanics, spectral theorem, and vibration analysis. That is, Hermitian operators represent observable physical quantities like energy, momentum, and position. So, measurements yield real values. Hence, it is the need for Hermitian operators. Then Hermitian matrices can be diagonalized using an orthonormal basis, useful in many physical and mathematical problems. In structural engineering and physics, stiffness and mass matrices are Hermitian, allowing modal analysis of vibrations. Next, let us see the application of unitary linear transformation. It is applied in quantum computing, signal processing, and computer graphics. In evolution of quantum states, yes, states is governed by unitary operators ensuring reversibility and probability conservation. In signal processing, Fourier transform is a unitary transformation helps to convert signals between time and frequency domains without loss of information. In computer graphics, it is used for rotation and reflection operations that preserve the norm of vectors. Finally, normal linear transformation applications. It is used in quantum mechanics, functional analysis, and control theory. In studying operators on Hilbert spaces, normal operators are a major class of interest. Normal matrices are used in simplifying systems using diagonalization. Then general framework for analyzing quantum systems with non-Hermitian but still diagonalizable operators. Uh, with this, with this, we come to the end of this session. Thank you.